Alright guys, we're gonna go over the equations of pharmacokinetics and just little things here and there just to, I guess, my input on it. So going over the easier ones, you got the zero order. These are going to be for the linear graph, and that'll be on the linear graph, and it'll be a straight line on the linear graph. And if you can tell, these two equations are pretty much y equals mx plus b format. So they kind of fit. If you look at it, they don't have any exponents on it. It's going to be a straight line if you want to read it like that. Also, another zero order equation is half-life is equal to 0.5 the initial concentration over the K. You just got to remember that the half-life for a zero order is dependent of the concentration. So you have to include the concentration within the formula. Make sure you guys don't get those mixed up with the first order. Now go into the first order equations. You have pretty much these two equations. They're practically the same. One's for amount. Amounts are typically in mass. And concentration is pretty much mass over volume in terms of units. They're pretty much the same. Just if you want to show work on which equation to use, and you want to use the preset equations they give you, just pick to the one that they're given to you. Like if they give you amount, you pick them, use the amount one, just to show that you know which equation you're using, and vice versa for concentration. Now these bottom two right here are pretty much the same as for the concentration one up here. So one has natural log and one has log attached to it. These equations are set up for if you want to find anything besides CT. So you're looking for, say, T or CO or initial concentration. I would recommend using one of these two equations. I prefer using natural log one because I was taught to use natural log. Log works just the same way. If you're going to find anything, like I said, you can find anything besides CT, I recommend just go straight into one of these bottom two equations. And if you don't know how to work natural log, because if you do natural log is CO of E of KT. This is actually the same as natural log of CO, then natural log of E to the negative KT. And that's going to be plus because they're multiplied together. And then for natural log, you can bring down the exponent, and natural log of E is equal to 1. So really you're just bringing down what the exponent is, so you're left with natural log of minus KT because of the minus here. And that's how you do that. But if you know how to do that, then it just makes sense just to use this equation here, because they'll take the offset that if you do try to do it and you do it wrong, then you're just better using this one. This is the same thing. And also, this is the half-life equation for first order. It's independent of concentration. So there won't be any concentration. What that means is that no matter what concentration you have to start with, the half-life for it will always be the same. Like I say, you want to go to 1/2, to 1/4. The concentration, that's just one half-life. That's the same time as the amount of, let's say, 1/8 to 1/16. It's going to have the same half-life regardless of how much initial concentration you start with. As long as you do a half from what you start with, or whatever value you start with, to half of that amount, it will be the same half-life regardless. You can't say the same for zero order though. But most drugs are first order, and I'm pretty sure we're doing first order when it comes to testing this first time. Now we go to Cl, or just clearance. The clearance formulas are pretty straightforward, except F. You should know that F is bioavailability. I don't know how to spell that, but yeah. So it's bioavailability. It's either ranging from like 0 point, like whatever some number, like to say lows is like 15%. That's 0.15, and then 100%, that's just 1. So as of right now, we're just dealing with injections, or we're just told to just keep it as 1 or 100%. So you can leave it as 1, or you can just take it out completely. It's the same thing. So you can just take that out, take this out. But for later, we're pretty sure we're going to use bioavailability, and we have to incorporate that in. But as of right now, just leave it alone. And the clearance equation is pretty straightforward. You just plug in what you have and swap it out. There's nothing much to go over there. All right, next is area under the curve. This first equation is pretty much the trapezoid method. Can I spell trapezoid? T-R-A-E-I-D. It's the trapezoid method. So what that means is that you have a graph, and you have points here, 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 and here. The trapezoid method is one of the most accurate way to measure the area on the curve, because you're incorporating the points within your calculations. What you're doing is that you're incorporating, let's say, this is point 1, and this is point 2, 3, 4. You're incorporating each point into your calculation of area on the curve. So what you're really doing is imagining it as a trapezoid, and within each point, you're making a trapezoid. And if you go back to algebra and find the trapezoid equations, space 1 plus space 2, 2 times height. This is the trapezoid like rotated over 90 degrees. The bases are the y values right here, and the height is your x values. So this is your height right here. So you can imagine it's tilted over. That's what a trapezoid will look like. And this is the general gist of how they came to that equation. And what you do is just you solve for each trapezoid, and then just end up adding it and so forth. So you have all the sides. It's pretty tedious, but that's how it is. The second equation, CPN over KE, that's more of a calculus concept, but if you don't want to know the gist of it, just skip over a little bit. But if you want to really know how they came to this equation, you start with CT equals CO equals AKT negative, and you take the integral of it. Pretty much in short, the integral of this will be CO e negative KT over K negative, and then you take the integral from 0 to infinity. And when you solve it out, you do the highest one first. What you do is plug it into the t. So you take that, negative CO e negative KT, or infinity to K, then parentheses minus negative CO K, then at 0 over K. Start from the left side. Conceptually, this right here is the same as this right here. So really, you're trying to find, you want to get in the graph, you're finding CT at infinity. And if you know pharmacokinetics, it won't ever reach 0, but it'll reach a number pretty much to 0. So in short, it's pretty much a 0 up top over k. No matter what, this whole thing is just 0. So you're really just dealing with this right side. And as you can see, it's at time 0. That's pretty much saying CO, or that's just anything to the power of 0 is just 1. So you're left with just CO. So this goes away pretty much. And keep in mind a negative and negative. You're minusing a negative, that's just adding. You're adding to 0. You're left with CO, goes K. And this only applies to a graph and you given just a straight graph. If you want to find a area in the curve for it, you take the value you found here, your initial concentration, and put in and divide by your K, and you'll get the AU, area in the curve. But you can find it for other points too. That's why it's really CPN, because you can find it, like say you want to find from here onwards, and you try to find this area on the curve, and it's a straight line, then you find that concentration at that time, and then plug it in, and you'll get the area under the curve from there on. So knowing that, this last equation will incorporate both the trapezoid method and this integral value right here, the equation. Because when you have the first order equation or graph, it ends up looking like this. It's not straight. So what you do is that you find it from the values that you do trapezoid method, and let's say you have like graph values of y and x, and it goes all the way to like 10 at x of whatever 40, like 20. And that's going onwards is extrapolating out to the right side, which you don't want to do, because when you do it in a semi-log graph, it ends up looking like a straight line, but it really is not a straight line. The semi-log graph is just straightening out the line, but it really isn't a straight line. So you're going past this point than what you're given, then you're extrapolating outwards. That's why you're using this value, this equation here, to find out the rest. Use the trapezoid method to find it up to, I guess it's safe to extrapolate to the initial concentration, up to your last value point, and then to extrapolate out to the right side to find this like area. And let's say the point stops here. You have to use this right here to solve out the rest. And you add it together, and you should get area in the curve from 0 to infinity. And that's about it. Oh yeah, make sure to include your units in your calculations. And that's all I gotta say.
Make sure you guys rate,
Oh God,
comment, and subscribe for some more content. Thank you.